Here we will see SAGA database pattern in microservice architecture. In a microservice application, each service has its own database. Therefore, a traditional ACID transaction cannot span multiple databases. The SAGA pattern is used to manage distributed transactions across multiple microservices. It is a sequence of distributed transactions where each step updates the system. The SAGA pattern ensures data consistency by dividing a large transaction into a series of local transactions. And if one transaction fails, the SAGA executes compensating transaction to undo the completed steps. For example, if you are purchasing from e-commerce website and if due to some reason inventory service fails, the payment must be refunded to customer. SAGA pattern can do this by refunding payment back to the customer and roll back the transaction. There are different situations when you can use SAGA pattern. First, cross-service workflows. When a business process spans independent services like payment, inventory and shipping. Then long-running operations. When a workflow takes time and holds strict ACID transactions, database locks would hurt system performance and availability. Then compensating action exists. When you can clearly define and undo a refund action for every forward step taken if any error occurs. Then eventual consistency tolerance. When your application architecture allows a brief window of intermediate states instead of needing immediate and rigid consistency. Workflow SAGA database service pattern is: first, customer places the order and order service creates the order. Then payment service processes the payment and inventory service updates the stock. And if no error occurs, the order is successfully completed. But if step 3 fails, that is inventory update fails, then refund payment service is updated and order is cancelled. SAGA pattern is primarily implemented in two main ways: choreography and orchestration. First, we'll see choreography SAGA pattern. A choreography based SAGA is a decentralized event-driven pattern for managing distributed transactions across microservices. Here, each microservice executes its local transaction and publishes an event, and other microservices listen to these events via message broker and decide whether to execute their own local transaction or trigger a compensating rollback action. Workflow choreography SAGA pattern is: payment service publishes its events after completing its task. Then inventory service subscribes this event and publishes inventory service events. After this, order service receives this inventory service event, complete its task and sends event to the notification service. Then orchestration SAGA pattern. Here a dedicated central service acts as a brain or controller of the transaction. It tells each participant service exactly what local transaction to execute by sending direct commands. And if the step fails, the orchestrator is responsible for executing the compensating transactions in reverse order to revert the changes. Workflow of orchestrator SAGA pattern is: orchestrator starts the transaction and calls each service in sequence. That is, it will call payment service, inventory service and order service. Then it decides the next steps and executes compensation if the failure occurs. Key advantages of SAGA patterns are: high scalability. Services executes local transaction independently without holding global locks of database roles. Then no resource blocking. Unlike traditional two-phase commit protocols, it avoids locking resources across network boundaries, which improves system availability. Then loose coupling. Services remain independent and communicate asynchronously via events or direct commands. Fault tolerance. Partial failures are handled cleanly using compensating transactions that roll back or undo complicated steps. And disadvantages are: lack of isolation. Unlike ACID transactions, intermediate states are visible to other operations because local changes commit immediately, which risks data anomalies. No automatic rollback. Developers must write custom compensating transactions to explicitly undo changes rather than relying on a built-in database rollback. And eventual consistency. The system is only consistent eventually, which means temporary discrepancies exist between services. And high complexity. Managing large step sequences, network timeouts and partial failures increases coding and maintenance overhead. And hard to debug. Tracing errors are tracking a failed workflow across asynchronous message-driven services, which requires specialized logging and correlation IDs.